Okay, so let's go around this way.
Okay, yeah. Actually, I didn't know that. I just knew you are a really famous particle physicist, but now you are also studying about the astrophysics, right?
Yeah, well, there's a strong connection between particle physics and cosmology and high-energy astrophysics.
So you're doing everything?
Not everything, but
All about physics.
yeah, it's all physics. Yeah.
Yeah, nice. Yeah, when I came here, it looks like a movie scene in Interstellar movie. It's the first time to introduce you in South Korea, so we are really proud of this. Yeah.
Actually, I did do some South Korean program some years ago.
Oh, really? Then let me say it's the second time to introduce you in South Korea. So there are a bunch of questions. Just feel free to say anything. So the first question is, how did you come to study physics?
I got interested in physics when I was about 12 years old. So I used to read a lot of books. I just got interested in how the world got to be the way it is today. But I'm not a good experimentalist. I'm a theorist, right? Yeah. So I studied mathematics and theoretical physics, and anyway, here I am. Yeah. I was one of the people involved in thinking about what experiments you could do with big colliders, and I got involved in that in about 1975. We studied what physics you could do colliding electrons and positrons, and then in 1984 participated in the first studies of the physics you could do with a Large Hadron Collider, so the proton-proton collider that's operating now. So the Higgs boson was something that colleagues and I started thinking about also back in 1975.
Wow. For Higgs boson?
Yeah.
Such a long time.
So we wrote this big paper discussing how a Higgs boson might show up in different experiments, which was the Higgs can decay into two photons, two particles of light. And this would be a very, very clear signal of the Higgs boson. And that was, in fact, one of the ways in which it was discovered in 2012.
The second question is, there is a perception that theoretical physics and particle physics are studies only for geniuses. So what do you think about this part?
It's always difficult for me to identify, what is a genius.
That's more better question.
To achieve results in theoretical physics, like in many other areas, you have to have ideas, but you also have to be prepared to put in the work to calculate those ideas. And so, the inspiration part you might want to call genius, but the rest of it is not necessarily what you would call genius.
I see.
But that's the way you get results.
And what is physics to you?
Of course, physics is the study of the fundamental laws that govern the behavior of the universe and have governed the behavior of the universe for 13.8 billion years, right? So for me, it's the most fundamental science. I apologize to those of you who study other sciences, but
it's okay.
For me, it's fundamental. It's also a way of life. My daily routine is centered around physics. Right? I wake up in the morning, I have my coffee, and I look at the papers. Yeah. Maybe I have some idea, or maybe I realize that some project that I'm working on we need to change. So that's the way I start my day. When I'm reading the papers in the morning, I first of all look at the titles, and then that sounds interesting. I look at the abstracts, the short descriptions of the paper, and then if it still looks interesting, then I look at the full text of the paper. And if it still looks interesting, I download it to my computer. Very occasionally, I will actually print it out.
I see. So it's a small question. So can you find the specific paper around here? Because I have no idea how can I find the papers around here.
It used to be very simple. because the more recent papers were on top.
There are laws.
So old one should be the bottom.
Right. I had what I called a geological filing system. There were sedimentary layers of papers. But now it's easier to find papers.
Right.
Has the way of studying physics changed a lot between the past and today?
Yes, I think so in various ways. So one is, of course, the importance of computers. So nowadays, if you want to do detailed calculations, you use a computer. I must confess that now I've got to the stage where I ask the students to do the detailed calculations. I think another thing that's changed is that physics has become much more global. Communications are much better now. Somebody writes a paper, they publish it electronically, then everybody can see it. The physics playing field has become much more level. Anybody, anywhere, in principle, has access to all the latest information. Of course, another aspect of that is now we're much more used to teleconferencing, to Zoom and other programs. We have lectures that are broadcast worldwide. Of course, we still have seminars which are held in person, and we still have conferences where people meet, and those play essential roles. But there is this additional means of communication.
Yeah, right. Actually, these days, there are a bunch of many virtual conferences around the world, right?
Right.
Maybe in the past, only some area, people studied physics.
Let's say 100 years ago. So you had conferences like the Solvay conference, very famous. You had maybe 20 physicists there. They would all be Europeans or maybe Americans, but nobody else, right?
I was not there.
I wasn't there either.
Okay, so this is a very fundamental question. Where does the mass come from?
Mass comes from... be a little bit more precise. The masses of elementary particles come from the way that they interact with the Higgs boson. So you have to imagine that the Higgs boson forms this universal environment throughout all of space, and particles travel through that environment. If they interact with that Higgs environment, then in some sense they get slowed down. They travel at less than the speed of light. So a photon, for example, a particle of light, does not interact directly with the Higgs field. So it can go at the speed of light, but particles with mass, they interact with the Higgs boson, with the Higgs field, and the amount of their mass is proportional to that interaction with the Higgs field. And the more mass they have, the slower they go. They always travel less than the speed of light. So that's what happens at the level of elementary particles. It's a bit more complicated when you talk about nuclear matter, lumps of strongly interacting stuff with quarks inside. Of course, the quarks get mass from the Higgs boson, but this other strongly interacting stuff makes an independent contribution to mass, which is not directly connected to the Higgs boson. So one has to be a little bit careful.
So the Higgs boson is only for the elementary level.
Right. So, for example, the Higgs boson gives a mass to the electron. And if the electron didn't have a mass, there would be no atoms, because electrons would travel at the speed of light and they wouldn't be captured by nuclei. And then there's this particle that's responsible for the weak interactions, the W boson, and that has a large mass, about 80 times the mass of a proton. If it didn't have a very large mass, the so-called weak interactions would not be weak. There would be radioactivity everywhere. Life would be impossible. The Higgs boson, those are two of the most important roles the Higgs boson plays. It makes the existence of atoms possible, and it makes life possible.
Anyway, if there's no Higgs boson, then electron will travel with speed of light, and there will be nothing, right?
Well, so that there would be no atoms.
No atoms, yeah.
You could still have nuclear matter.
Okay, yeah. Actually, I thought you were looking like a Jedi in Star Wars.
Well, as long as I don't look like Darth Vader.
Okay.
Well, I started studying the dark side of matter before Star Wars. So.
Okay. Okay. So you are better than Jedi. So how's your opinion about dark matter?
So it's a big puzzle, right? We don't know whether dark matter is made of individual heavy particles, or whether it's made of something perhaps a little bit like the Higgs field, some sort of wave of matter which extends throughout all space. So in the case of the Higgs, it seems to be, if you like, flat, universal, homogeneous, isotropic. But it could be there are other analogous fields which sort of are wavy, like waves on the ocean, right? And then these waves would have a density, they move relatively slowly, and they could contribute what we think of as dark matter. So there's basically two classes of experiments looking for dark matter. They're the ones that look for the individual heavy particles, like what we do at the LHC, and then they're the ones that look for these waves of dark stuff. So I'm also involved in one of the experiments looking for these waves of dark stuff.
Oh, what was your favorite moment while working at CERN?
Well,
Is there no good moment in CERN?
Or quite many.
obviously one favorite moment was the discovery of the Higgs boson, which occurred precisely 11 years ago today, right? Because today is the 4th of July.
Oh, really?
So today is the 11th birthday of the Higgs boson.
Today?
Today. Exactly.
Really?
대박.
So today is really important day.
Yeah.
Okay, so we should take a picture together after this interview, right?
So that was a big moment, the discovery of the Higgs boson. I was fortunate enough to be in the CERN auditorium when the discovery was announced, and Peter Higgs was there, François Englert, who proposed similar ideas. He was also there. They got the Nobel Prize later on. So it was a real big moment, right? But actually, personally, one of the most satisfying moments occurred in 1979. I was talking earlier on about the strong nuclear forces which hold quarks together inside nuclei. And I was saying that most of the mass in the universe, the visible mass, is in the form of nuclear matter. And it comes from these, lumps of strongly interacting stuff. So what holds this strongly interacting stuff together? There's a fundamental particle, a bit like the photon, which is called the gluon, which holds quarks together. Okay. Back in the 1970s, theorists were pretty sure that this thing existed, but it hadn't been discovered experimentally. And so in 1976, we proposed an experiment, how to look for the gluon. And the first results came in 1979. So for me, one of the most exciting moments was when an experimentalist showed me the first picture of a gluon.
How's your expectation about what the next big discovery in the future CERN experiment will be?
I don't know.
You should know.
Yeah.
Then who knows?
And there's this saying, if we knew what we were doing, it wouldn't be research, would it? Well, let me tell you a story. I think it was 1982, Mrs. Thatcher, who was the Prime Minister of England, came to visit CERN. She asked me, what do you do, young man? So I said, well, I'm a theoretical physicist. My job is to think of things that the experiments might look for, but then I hope they find something different. And so Mrs. Thatcher liked things to be the way that she wanted them to be. So she said, wouldn't it be better if they found what you predicted? So I try to explain that if all that is found is what is predicted, then you don't have clues for what comes next. And so I think we're somewhat at that stage. So we found the Higgs boson, great. But now we want to know what is next, but we don't know.
Okay.
So it might be dark matter particles. It might be more Higgs bosons. It might be a new heavy particle which generates new interactions. I don't know.
Yeah.
Personally, I'm interested in the search for these heavy particles of dark matter. So I'm interested in both the searches for heavy particles, and the searches for waves of light particles. Nowadays we look back and we think, well, obviously the Higgs boson had to exist, but it was not so obvious at the time. And there were some people who said, well, there's no elementary particle called the Higgs. Stephen Hawking famously bet that the Higgs boson didn't exist.
And did you fight with Stephen Hawking?
No. It would be an unfair fight. He's much smarter than me.
How did you confident about that Higgs boson will exist at that uncertain period?
So I was pretty confident because I spent a lot of time looking at the equations of the Standard Model. You needed something, either the Higgs boson or something which did the same job as the Higgs boson. And the more you look at it, the more convinced you get that the simplest answer is the Higgs boson.
And do you think there is a possibility of discovering new particles experimentally soon or in the future?
Well, certainly I think at the LHC, the Large Hadron Collider, there's prospects. We'll be continuing to operate the LHC for many more years. It'll get a lot more data. And experiments also are getting more and more clever about the way to look for new particles in places that they couldn't observe previously. And there are possibilities, for example, that that supersymmetry, one of my favorite theories of new particles, could be hiding at the LHC in a place that we haven't looked yet. And so that's one of the things that I work on.
Actually, there are those who say that new discoveries in particle physics are not expected now. So what do you think about this, and where can new breakthroughs come from?
So people who say that, I would ask them very politely, so what do they think dark matter is? Right. Some people might say, well, there's no dark matter, we have to modify the theory of gravity. That's a really, really ugly theory, very difficult to make it consistent. Much simpler to think that there's some new type of particle, maybe more than one type of particle, that we haven't discovered yet that makes up the dark matter.
This is really clear.
It's so clear.
If a 100-kilometer long particle collider were built, what new discoveries do you personally expect?
So I think that would have very good chances of producing dark matter if we haven't already produced it at the LHC. And it would also enable us to make much more precise measurements of the particles of the Standard Model. It would help us understand what might lie beyond the Standard Model. I have some ideas, what I think might lie beyond the Standard Model. So I've already mentioned particles of dark matter, I've already mentioned supersymmetry. So all these things might show up either directly or indirectly in a 100-kilometer accelerator.
Okay, so what would you like to say to friends who want to study physics?
Go for it. I think everybody should try to do what they want to do, rather than listen to what somebody tells them to do, and do something which they don't really like. If you like physics, study physics and go for it, right? And maybe physics is the right thing for you, maybe it's not the right thing for you, but because you enjoy it, you will be happy.
I know you do a lot of work connecting science and the public. So do you think it's important for the public to know science or physics?
Absolutely. So I think, for many different reasons. So one reason is that science in general and physics in particular provide the rules by which the universe works. And I think it's important that as many people as possible understand what science is, understand how science works, understand how the universe works. That's just for the healthy running of society. But then I think it's also important that different parts of society engage with each other. I think it's important that people who work in science engage with people who don't work in science. Also, I think it's important that we who do work in science listen to what other people have to say, right? Because maybe there are things that they don't understand or things that they want to understand, maybe things they're not happy about. And so I think the way to address those issues is to engage with them, talk about what is the science that we do, and listen to their questions and answer them as best we can. And then finally, who pays for doing science? It's the people in the street. They're paying for it with their taxes. And so I think that we have a moral obligation to share with them what we're doing, why we're doing it, and what we're discovering.
You're right, yeah.
People should know that. Yeah.
Maybe this will be a last question. I heard that you worked with Benjamin Lee before, and do you have any memory with him?
So I never worked directly with Benjamin Lee.
I see.
So I worked with Mary Gaillard, who did some very famous papers with Benjamin Lee. And much of my early work was really based on what Benjamin Lee did. So I met Benjamin Lee when I was a student. I was a student in Cambridge. He came to Cambridge. He gave a seminar. I went and had coffee with him. So I had the opportunity to hear him and hear his ideas. He played an absolutely crucial role in establishing the ideas of Peter Higgs and this whole structure of the way the Standard Model works. He gave a very famous talk at a conference in Fermilab outside Chicago. Let's see, when was that? 1973 probably, which really put the ideas of Peter Higgs on the map. So he played a really key historical role. Unfortunately, he was killed in a freak vehicle accident shortly afterwards. Otherwise, I think he would have had an even more famous name than he does today.
Thank you for letting us know. Okay, actually, we finished our prepared question, but my other personal question is: do you think if he can be one of the best science YouTuber in South Korea or not? Do you have any opinion for that?
Well, I'm afraid I'm not familiar with many South Korean science YouTubes.
Yeah. It's just a joke, actually.
Yeah, but you've got lots of questions. You've well prepared. Very important to, as we were discussing earlier, communicate with the general public. And the most effective way to do that, I think, at least initially, is in a relatively informal way. You don't start writing formally on the blackboard, right? You start chatting like among friends. That's the way to do it.
Actually, in Korea, there are people who studying physics decreasing in South Korea.
It's really sad because most of the students now are becoming a doctor, medical doctor, not physicist.
Well, I mean, we need doctors too, right? I think these things come in waves. The numbers go up, numbers go down. So I've been working at King's College London for almost 13 years now. I've seen the numbers of students studying physics go up quite substantially. The physics department has grown, and it's a great place to be. What I would say is that South Korea is very, very famous for engineering, both sort of large-scale engineering, but also electronics engineering. I understand that Korea is very good at that, and it's very natural that people would be attracted to that. I think the attitude of the government is to encourage people to be interested in fundamental science. And certainly they've been very supportive of what we do in particle physics.
And I heard that you were appointed the commander from British Empire, right?
Right.
And can I ask you, how can I get that?
The first thing is you need to be a citizen of the British Empire.
Yes, right. Maybe I have to be British.
Well, no, I think it's okay if you're like Canadian or Australian.
I see. Yeah. Okay. Yeah, thank you. Thank you for giving us.
Thank you for having us in.
You're welcome, and thanks for your interest.
Thanks so much. Yeah. You are a living legend.
Well, I don't know about being a legend, but at least I'm living.
3, 2, 1. Thank you. 여기가 지금 빔이 들어가는.
교수님 어떻게 하다가 이 좀 반물질 쪽 연구를 하게 되셨어요?
칼로리미터 히스토리에 도전하는 이러한 목표를 세우고 있습니다.